Yep, so today we are going to start a new section, which is called iterative methods, iterative techniques. So we are going to find approximate solution to this linear system. So if you deal with your PC, if you use your PC to find solution to this system, that means you are finding approximate solutions. Always approximate solutions, not exact solutions, right? So if you deal with, if you use your PC or PC to find this, to find solutions to the system, that means you are finding approximate solutions, right? Okay, so this is another technique. Earlier we discussed Gaussian elimination method. So it is called direct method, right? So Gaussian elimination or Gauss-Jordan method or Gaussian elimination. So those techniques are called, known as direct methods. So in those methods, we considered both the coefficient matrix and the right hand side of the system together. The matrix, this matrix is called the augmented matrix. So we store this matrix on the memory of your PC, right? So we perform row operations to reduce this matrix to an upper triangular matrix, right? So all the time you have to change this entire matrix. All the time you have to change and store into the memory of your PC, right? All the time you change this matrix by performing your operations, right? And you have to store all zeros in this matrix also. Yeah, you have to store these zeros as well. So the cost of computation is larger than large than this method, I think. Right? So you have to store all zeros to the memory of the computer. Yep. And and you always change this matrix by performing row operations. So that is that is the so that is one of disadvantages of direct methods. So you have to, so if your system is huge, let's say this is a million by million, A is a million by million matrix. So then, you have to use a large capacity of your computer to store this matrix, augmented matrix, and all the time you change this matrix by performing, when you perform row operations, always so if you perform, let's say you want to remove this guy, let's say this is 5. Yeah, if you want to remove this guy, you have to perform row operations, right? Then after performing that operation, you have to store this matrix. Then after that, you are changing this matrix again to reduce, to get an upper triangular matrix. Always you use the memory of the computer, and so the computational cost is large, very large when you use direct method. So Gaussian elimination techniques. Yeah. So, but however, if you use iterative methods, you can reduce the cost of computation drastically. You can reduce that, right? So you don't need to change. You don't need to change this matrix all the time. Once you store this matrix A into your computer, that's all. That's enough. Yep. So you don't need to touch this matrix always. So if you store matrix A into your memory of the PC, that's all. Yeah, you don't touch this matrix. It remains the same way. It will be the same always. But in the direct methods, right? In the direct method like Gaussian elimination or Gauss Jordan, yeah. So you change this matrix all the time, all the time. Then you have to store, or yeah, always change this matrix and store. Change, store. Like yeah. So after performing row operations, if you want to reduce, if you want to get rid of these elements, let's say this is the diagonal. Yep. So if you have a non-zero elements here, so yep. So let's say you want to vanish this, you want to yep. So remove this guy. There you have to perform row operation. After performing that row operation, you have to store this matrix. Yep. So always so this matrix is changed all the time all the time in when you follow Gaussian elimination. But so if you use iterative method, right? So if you don't need to change this matrix, it is fixed. A and B are fixed. Yep. So A matrix, A coefficient matrix is and B is fixed. Don't need to change all the time. That means you can reduce the computational cost. So computational cost is not that expensive compared to Gaussian elimination, Gauss-Jordan methods. Okay, so that is one of the advantages of using iterative methods, right? So one of the advantages of these methods, iterative. That's the difference between direct methods and the iterative methods. In direct methods, so you always change this augmented matrix and get something. Get something. Get something. Get a matrix which is an upper triangle. So so you need a lot of memory to work out the system using Gaussian elimination. But on the however, so if you use iterative techniques or methods, so you don't need to change matrix A and B all the time. If you store matrix A to your memory into the memory of the PC, that's all. That's all. You don't need to change A and B. You don't touch these matrices. So you don't change. Yep. So you don't perform here. You don't perform row operations. Okay. So then you can reduce round of errors. So many things. The computational, I think if you count the number of operations in Gaussian elimination method, so I think it is about order of n cube. You count the number of operations when you use a Gaussian elimination method. It is about order of n cube. This one, so if you use iterative methods, you get a lesser number of operations. I according to my memory, I think. So it is about n squared. Yep. So O of n squared. Yeah, I think so. Yep. So O of n squared. So the number of operations will be, you can reduce the number of operations if you use iterative methods. That means the computational cost is a little bit lesser than the Gaussian elimination one. Yep. So got it. So that is one of benefits using iterative methods. All right. Yeah, so if you deal with sparse matrices, let's say if you have a system with, so let's say this is a large matrix, let's say A is a large matrix, having a lot of zeros in that matrix, right? So these techniques, I think it is worthwhile using this technique if you have a large sparse matrices, right? So because we don't need to store these zeros, if you have zeros in the coefficient, if you have a lot of zeros in the coefficient matrix, so you don't have to store these all zeros. But in Gaussian elimination method, you have to store all these zeros. So then you have to use a lot of memory in the computer. But if you use iterative techniques, you don't need to store these zeros. You just consider the non-zero values. So that is another benefit. Another benefit of So of this iterative method. You don't need to store the zeros in the augmented in the coefficient matrix into the memory when you use iterative. But if you use Gaussian elimination method, you have to store all zeros of the matrix, right? You have to store all the matrix, coefficient matrix with the right hand side. But if you follow the iterative methods, you can ignore these zeros because so no zeros, you don't need to store into the memory of the computer, so you can store the non-zero values only. Then you can reduce the computation cost. Or memory capacity, you can say memory capacity of the computer, then you can use that capacity to do the computation efficiently. Then we can get we can get a solution effective. We can obtain solutions very fastly, I think. So because we don't store all zeros of the entire matrix. If you have a sparse matrix has a lot of zeros, so we don't need to consider these zeros. We don't need to store these zeros in if you use iterative method. But if you use Gaussian elimination, you have to store all zeros into the memory of the computer. Then the memory capacity will be reduced, I think. So if you store everything in this matrix. That's the difference between the direct method and the iterative method. Right? So this method is efficient. This method is efficient for large systems. For large systems, this method is efficient compared to Gaussian elimination. So I think you understand why it is efficient, because in the Gaussian elimination, you have to store entire matrix A. But here, iterative method, you don't need to. You can ignore these zeros. Yeah, let's see how it happens, right? Any questions, any doubts? Did you understand? Okay. Okay, let's discuss iterative methods. So how do we go? Yeah, so how do we use these iterative methods? All right. So iterative, if you use iterative methods, right? So you always start off with an initial guess or initial approximation of of the exact solution. So we start off with an initial guess. You have to guess the solution, right? So yeah, you can put any educated. So let's say yep. So yeah. So you can start off with some initial guess. So this one. So we assume this would be the solution to that approximate solution to x equal p. Yeah, and we improve this. We improve this. So we improve or we refine this solution, approximate solution. So in the first iterative, so we start off with this initial guess and put this one into the system and we obtain the next iterative. So this one is much better than the previous one. We refine this solution. So these are all approximations to exact solution. Let's say this is the exact solution. X star is the exact solution to this system, right? So these are approximations to this exact solution. We start off with initial guess. Yeah, we start off with this. Then we refine this solution. So one by iteratively. We refine this solution iteratively. Okay. So let's start off with this. Put this one into the system and get the next iterative. So this is the first iterative. So this is the initial guess. This is the first iterative. This is called first iterative. And using this first iterative, put this one into the system. Then we can obtain the next iterative. So which is this one is much better than the previous two. Yep. So that means this one is close to slowly. Don't know whether this sequence converges to the exact solution. We are using iterative methods. Let's say we follow one of methods, right? One of iterative methods. So we always generate a sequence of approximations of this exact solution. So these are this is a sequence of approximations of the exact solution. This is the exact solution to this system. So these are see this is a sequence of approximation. Third, so third iterative, fourth, da da da. If you you can generate so approximations. Let's assume this sequence converges converges towards this exact solution. So we can then what happened to the length between distance between these iteratives and this. Then if you find the norm, so this is a kth iterative. So kth iterative, and this is the exact. If you will realize that this norm is getting, this norm is going to zero as k tends to infinity. That means this sequence of approximations of this X star converges to exact solution of this system, right? So if you follow one of iterative techniques, you always generate a sequence of approximations. Don't know whether this sequence converges to exact solution. I will later explain the conditions, the convergence of this sequence, right? So what are the conditions? Should be satisfied to converge to the exact solution. I will explain that later, right? So, right. So if you follow iterative method, you generate a sequence of approximations, right? Like this. If this sequence converges to X star is the exact solution of the system, then you can, if you find the norm of, approximation and X star, then what happened to this difference between these two? Norm of these two, difference of these two is decreasing to 0 as k increases, as k goes to infinity or as k increases. So this distance is getting smaller, closer and closer, getting small. That means this one approaches close to getting close to X star. Okay. So so this one is important here. During the iteration, the matrix A does not change. But in the Gaussian elimination, so you have to change this A all the time. You have to change the matrix all the time. So that's why you need a lot of computational cost. Cost is very expensive if you follow Gaussian elimination. This is cheap. So if you follow iterative method, so you don't need to change. You don't need to touch this matrix A and B. Don't need to change A and B. So, all right. So that's the biggest advantage of this iterative method. Each iteration involves matrix vector multiplications. Efficient. I think you understand. We don't need to store all zeros into the memory. So we can ignore zeros in the coefficient matrix. Then we can consider only non-zero elements. If you have a sparse matrix, then this method is very effective compared to Gauss elimination method. Because if you use Gauss elimination, you had to store the entire A, and you change all the time. You change this matrix all the time by when you perform row operations. You change and you have to store the entire matrix into the memory all the time after performing row operation. Then you store this entire matrix into the memory of the computer. So always. So yes. So we start off with an initial guess. How do you perform? How do you use this method? You have to start off with an initial guess, right? Then you generate a sequence of approximation, right? Approximations. These are approximations to this exact solution, right? We start off with an initial guess, then we generate a sequence of approximations. Okay, so each iteration produces. So this is this is first iteration. This one. So this is this one. This iteration is second iteration. So each iteration produces a new refined approximation of the solution. Yeah. So if you substitute this one into here, then you produce this refined approximation to exact. And then you use this to produce the next refined approximation, right? And you use x2 to produce the next iterative next. So this is refined, better than previous. If the sequence converges, right? If the sequence converges, this one is much more refined than previous derivatives, right? Refined. Okay, so I will explain the condition. So I think the convergence depends on this matrix, right? If this matrix is strictly diagonally dominant, so this sequence converges to exact solution. If so, you have to check whether this matrix is strictly diagonally dominant. I will explain what strictly diagonally dominant is later, right? I just say the condition if this matrix is diagonally or strictly diagonally dominant, this generated sequence converges to exact solution. That is the condition, right? That is the condition. We will prove that condition as well if I have time. Yeah, we will prove that. Yeah, so here, this is the condition. So yeah, we will prove that. Yeah, so in next slides. So using iterative methods, we can generate the sequence. We don't know whether the sequence converges to exact solution, but that sequence converges to exact solution whenever this matrix is strictly diagonally dominant, right? We can show that, this sequence converges to exact solution whenever this matrix is strictly diagonally dominant. Yeah, so that's okay. But the convergence, right, is not always guaranteed, right? It depends on this matrix. If this is strictly diagonally dominant, this sequence converges. Otherwise, it is not guaranteed, right? If this is not diagonally dominant, we cannot say this could be converges to, this could be converging to exact or not. We cannot guarantee. We definitely say, we can definitely say this sequence converges to exact whenever A is strictly diagonally dominant. Okay, got it? Got it? So this is the theorem, right? Convergence theorem. If your matrix is strictly diagonally dominant, it should be strictly. So otherwise this is greater than or equal. Yeah, strictly diagonally dominant. Yeah, so then the sequence we generated converges to the exact solution of the system. Yeah, AX. Yeah, so this. If A is not diagonal dominant, right, may we are, so it is not guarantee up, so it may still converge, but there is no guarantee up. So don't know whether it converges or not. But if this matrix is strictly diagonally dominant, yeah, so we can definitely say, yeah, so this generated sequence generated sequence, yeah, so converges towards converges toward the exact solution. Yeah, so this could be any initial guess. Yep. So this is true for any initial guess here. For all initial guess, you can give a wild initial guess, right? But anyway, your generated sequence converges to exact solution whenever A is strictly diagonal dominant. Yeah, we will come to that. Yeah, so okay, we rearrange this equation. All right. So we rearrange this equation to get this form here. Just rearrange. So we rearrange this equation. You can get lower triangle. You can break. So you know that matrix A is equal to lower triangular plus upper triangular plus the diagonal B, diagonal matrix. So you can not decompose, you can write A in this way, right? Rearrange this equation, then I can use, so can use so, diagonal, only diagonal part I fill with zeros. So this is the D is the diagonal of A, and other entries I fill with zeros, right? So D is that. This is upper triangle of A, lower triangle of A, right? So I just rearrange this equation. This is my A, and this is my X, and the right hand side. Then I can put these two to other side, and like that you can rearrange this equation to this form, right? Right. So this is almost like so this is a function of another function. This is a function of X. I can so I can label as g of X here, right? So X is equal to g of X. Actually this is actually this is fixed point iteration. Yeah, so I think you have learned uh, numerical analysis. You are still learning, right? So this is you can put fixed point theory to find the solution of this equation. Fixed point theory to find. So we use fixed point theory to find the solution to this. So this is the previous iteration. I will put K here. So if you have your initial guess, you start off from here. So this is 0. Then you will get the first iteration. Then you use that iteration to to get the next iteration like that. Right? So basically you rearrange this equation to this form. Then you generate the sequence iteratively. Right? You generate the sequence of approximations iteratively, right? Right. So so that's how we generate the sequence. Then we have to check whether the sequence yeah, you can, if you know the exact solution of this sequence, then you can measure the norm. You can, yeah, you can measure the difference between these, yeah, approximations with the exact solution by computing the norm of, yeah, norm of this. So if this is the sequence converges to the exact solution, so what happened to this norm? This norm is reducing to zero as k increases. As k increases, this norm is decreasing to zero. Yeah, as k goes to infinity, yeah, this norm decreasing to zero. All right, so this F and this E, uppercase E and F, yeah, depends on the type of, yeah, you can change, you can consider different. So there are different derivative methods. So one of, so these are methods: Jacobi iterative method and Gauss-Seidel iterative method, SOR iterative method. There are many iterative methods, right? So for those iterative methods, yeah, so I think so, yeah, so these two, yeah, matrices E and F, yeah, change according to the iterative method you use. If you use Jacobi iterative method, yeah, this one is something else. Yep. So if you use Gaussian, yeah, this will change. These two will change. Yeah, this matrix E and F, right? So let's discuss, so this is the simplest, iterative method, and Gauss-Seidel is the refinement of Jacobi's method. And this one is the most refinement method of these two. Yep. So let's discuss the Jacobi's method, iterative method first, right? So let me discuss Jacobi's method. Okay. So this, let's assume this is your system of equations. Yep. So here we have how many? One, two, up to n number of equations. How many variables? One, two, same number of variable unknowns we have. Then coefficient matrix is a square matrix. Okay, this is the right hand side. Okay, all right. Okay, we start off with some initial guess. Yep. So this is we assume. Let's assume this would be the first guess or first approximation to the exact solution of this system of equation, right? Yeah, we start off with this initial guess. Right? These are vectors. Yeah. Okay. Okay. So we can start off with like this. Yep. So that's So if you have some any initial guess, right? Okay, let's put this one to obtain the next iterative, right? Using Jacobi's method. So we follow the Jacobi's method now, right? Yeah. Okay, let's substitute this one to get the next iterative, right? So I will isolate these variables. I will isolate x1 of the first equation. Then I put these terms to other side. Then v1 minus these terms. And let's assume this is not equal to 0, otherwise you cannot find x1. If you have 0 on the diagonal, so you will get Yeah, so you have to interchange that, right? Make sure that this is not equal to 0, otherwise you cannot divide the equation by this number, right? So important, you have to, if you follow the Jacobi's method, make sure that there are no zeros on the diagonal, right? Okay, okay. Then, okay, x1 is equal to b1 minus these terms. Everything divided by this a11, right? Okay, then you can find the first iterative by substituting your initial guess into, yeah, so just put this, yeah, to find the first iterative, yeah, so this is x1 in the first iterative, in the first stage. This is stage number 1. So this is the, you will see the stage here. So this is the stage number, right? This one, this is the stage. This one is the k plus 1 stage, and this is the kth stage, right? And this index is the variable, but yeah, x1, x2, and so on, right? So this is the stage, right? Stage, 0th stage. So you have to yeah, give a good guess for this stage, 0th stage, and put this one to get the next solution in the first stage, right? Yeah, you can plug this now, yeah, this vector into here, then you can obtain the solution in the next stage, is the first stage. Okay. Yep. So then we can find, yeah, x1, and similarly, yeah, then you can isolate, yeah, you can solve this for x2. So you put other terms, other remaining terms to other side, b2 minus other terms, right? And divided by, yeah, so a2, yep, so make sure that this is not equal to 0, right? Unless if you use Jacobi's method, yeah, so diagonal, so these elements are not equal to 0. Yes. Then you can find the solution in the first stage using this. Yeah, plug this, yeah, this one into here, yeah, into there. Then you can find the solution in the first stage. Yeah, so this, like that you can find all x1, x2, xn. Yeah, so that means if you write in this notation, you found, yeah, the solution in the first stage. This is the first stage, and these are the solutions. You can write, so x1, yeah, so x1 first stage, yeah, first stage, in the first stage, x2 variable. Then you can use this one to find the solution in the next stage, x2, second stage. And we do iteratively, so then we can generate a sequence x0, x0, x1, yeah, x1. So this is the stage number, 0 stage, first stage, second stage, and so on and so forth, right? Like that you can generate a sequence. Okay. Yeah. So I have so I wrote a octave code for that. Yeah, let me Jacobi's method. I think the practical session, I think they will explain this code, right? I just use this code now to to explain this Jacob, yeah, this system. Yep. So here So here we go. So let's let's use Jacobi's method to obtain a sequence of approximations, right? So they start off with this initial guess. Yeah, you can you can do experiment. You can change the initial guess and see whether the sequence converges to the exact solution. Ah, this is the exact solution. If you plug this one into here, you will realize that this satisfies this system, right? So this is the exact solution, right? And this is the initial guess, right? So let's use our program code to generate the sequence of approximations, right? So I will use my code to generate the sequence of approximation. So here I start off with so this is a function. Yeah, so this is the function name, right? Then I use and I had to so I had to define a b as I said before, I had to store matrix A and B and your initial guess this is your initial guess, and this one is the maximum iteration. It's the number of iteration, maximum number of iteration. Yeah. Can you put the code in the chat? So I will put so copy control A my keyboard is then you can you can play with this code. I think in the practical session they will explain this code, and so I will copy so everybody. So yes, and so you have the code now. So let's play with this code. So this is a function, right? So function name is this. You need function name to execute this code. Okay, and first of all, you have to define matrix A, the right hand side, and the initial piece represents the initial guess, and max is the total number of iterations you are going to execute. Okay, this is let me take my keyboard tab. So keyboard, keyboard. So I have external keyboard here, so so clear. So I will define this, I will store the matrix A. I store matrix A one time into the memory. So A, uppercase A. So I will store this, 2 space -1 space 0, break, the second row -1, 2, and -1, third row 0, -1, and 2, right? This is my matrix A, coefficient matrix, and I will enter the right hand side as well. Right hand side 0, next row 1, next row 2. So this is the right hand side. Okay, right hand side, and the initial guess, what is mine? So this is my initial guess. I denote it as P. The initial guess would be 0, break. because these are vectors, column vectors, right? 1/2, or we will get round of errors. So that's why that's the thing. Always we get round of errors. So so this is the initial guess and the maximum number of iterations. So max would be, so we can change. Let me put 10. Now I will, so because this is a function, so I store all matrices, coefficient, right hand side, and initial guess, and so I store everything. Because this is a function, I have to call, I have to call this function. So for the function, then I insert a p, what is the order, or a bp, p max, p max. If you want to execute, you have to call this function. That's here we go. Okay, so this is my initial guess. Start off with this, and this is the first iterative. I think this is correct. First iterative, second iterative, third. So first iterative, so 0.25, second, third, and when you, 8. See, what is the exact solution? Exact solution is 1, 2, 2. Okay. It looks like, okay, converging. Looks like that converges to. Let's increase the number of iterations. Let's increase the number of iterations. Let's say 50. Then let's. Okay, right. Converge. So, all right, after this is 31st stage or 31st iteration, we get this 32nd, 31st, sorry, 31st, after, okay. All right, so according to this precision, let's assume we have only how many? 1, 2, 3, 4, 5, 6. 6 significant figures. So decimal numbers, 5 decimal numbers. According to this arithmetic, let's say, so this iteration converges to, after 37 iteration, so we can see the sequence converges to, so we get exact solution after 37 iteration. So if you change the initial, let's change the initial condition. Let's try to, let's give a while initial condition. Let's put 100, something like that. 1000. This is negative while. This is a while initial condition. Maybe not even. So let's start off with this while initial condition. What happened? You can play with this code, now. What happened? Oh my god. Here we go. I start off with that. naughty, nasty initial condition. Yeah, 1000 minus what happened? Then this is the first iteration, getting improved, refined. So better than previous one, yeah. So make sure, yeah, this is our exact, right? Let's see whether this naughty initial, we start with this nasty initial condition, but using Jacobi's method, iteration method, what happened? So slowly, slowly, yeah, slowly here, yes, slowly after, yep, so that depends on it. So after, we should increase the number of iterations a little bit. Yeah, so after, well, you can see that after 54 iterations, not, yeah, unstable, yeah, going up and down, yeah. Yep, so after 65, yep, so iterations, yep, so slowly converges to, yep, so the sequence converges to exact solution. Yeah, that depends on this, yeah, so the reason is this matrix A is strictly diagonally dominant. So let me define the diagonally dominant. This is the right time to explain the diagonally dominant matrix. So you have to consider a lot of iterations to converge. This is slow compared to other two. So this is much better. Gauss-Seidel is the refinement of, improvement of Jacobi's method, right? So this takes, you have to run a lot of, you have to consider a lot of iterations to convert sequence. This is slow compared to these two, right? So you will, you can play with these codes and and you can change the initial condition, can give a wild guess, see whether the sequence converges to the exact. Yeah, so this is the simplest one. And this is the rate of convergence is very low compared to other two. Right. So let me define the diagonally dominant matrices. So yes, that diagonally dominant. Yeah, this is the right time to do. Yeah. Yeah. Talking about the diagonal dominant, strictly so if you consider strictly, then we don't have equal sign. If it is diagonally dominant, you put greater than or equal. So this is the diagonal element. Diagonal or element is the dominant term when compared to other terms. If you take the sum of diagonal elements, here we always consider the magnitude. Magnitude. We are not interested in the quantity, right? Quantity. We don't consider the sign, right? Sign. That's why we put magnitude, right? So this is the diagonal element in each row, right? AII, same column number and row number. The magnitude of the diagonal element is the dominant compared to sum of diagonal elements. Yep, so why? So here we have only one of diagonal element in the first row. So this is the diagonal element. One is not bigger than the sum of diagonal. elements. Here we have only one off diagonal element because this is 2 by 2. So 1 is not greater than or equal to, yeah, this one. Yeah, this is not diagonal dominant. Yeah, so yeah, this one, this row, if you consider, this is true. This should, yeah, for all i's, this should, I had to check, yeah, magnitude of all other elements. Yeah, for all life, you had to check all rows. Yeah, this is diagonal dominant. Yeah, so sum of these two is 2, and this one is bigger than that. But this is the diagonal element. Let me zoom in. Yeah, diagonal element is not dominant, right? Sum of diagonal element is bigger than diagonal. This is not diagonal dominant. Let's look at our matrix. Oh, where's my matrix? Yeah, this is my matrix A. I can say, yep. So this is dominant. Yeah, so 2 is bigger than sum of, yeah, magnitude. Always consider the magnitudes. All are magnitudes, right? 2 is bigger than 1 plus 0. Yeah. This is, we can say this is diagonally dominant, not strictly diagonally dominant, right? So sum of diagonal elements is equal to 2, which is same with the diagonal magnitude of diagonal element. Yeah, this matrix is diagonally dominant. That's why then the all iterative methods, all three, Jacobi, Gauss-Seidel, and so on. If you follow any method, then the generated a sequence of approximations converges to the exact solution because the coefficient matrix is diagonal. If this is strictly diagonally dominant, then it is much better. Strictly diagonally dominant should be strictly, yeah. So now we are going to talk about Gauss-Seidel method. So earlier we learned Jacobi's method, which is very simple and the convergence rate is very low, right? But if you can improve the convergence rate by changing small thing, okay? In the Jacobi's method, I think Gauss and Seidel saw that change here. Here, look at this. Here in the first equation, you use you find x1, right? Right. So you here this is your initial guess. Yeah, this is your initial guess. Zero stage. Yep, zero stage. Initial guess. To generate the solution in the first stage. Yeah. Okay. So yep. So then x1 is this one, right? Then how do you find the solution in the first stage? So this is the stage number, first stage. Yeah, you have to plug this initial guess into this. Yeah. So then when you plug this one into this, then you get x1 in first stage. Okay. So Jacobi didn't use, so he already has this number, right? X1 in first stage. So to compute X2 in X1 stage, so he didn't use the most updated value of X1. So this is the most updated X1. This is the outdated. So this is the value in zero stage, and this is the value x1 value in first stage. Gauss and Seidel used this value to compute x2 in first stage. He didn't use x0, x1, x1, 0. He used x1, 1. That's the difference. That's the slight difference. That's the slight difference. Yeah. So Gauss and Seidel, instead of using the outdated value for x1, so he already computed x1 in first stage. He used this, he used this most updated value, value of x1 to compute x2. Yeah, this is not okay. Yeah, so this is x1. Okay, yeah, let me go to that. Here we go. So, right, so this is our initial guess. And yeah, so this is x1. Yeah, anyway, you have to use all, yeah, so this initial guess to compute x1. After computing x1 in first stage, to compute x2 in the same stage, he used most update value of x1. He didn't use this all value of x1. He used most updated value in x1 here. This one here. Others are all values of x3, xn. Now he has x1 and x2 in this stage. To compute x3 in this stage, he could use most updated values for x1 and x2 to compute x3. And let's say xn, then he can use x1 in this stage, x2 in this stage, up to xn minus 1 in this stage, instead of using all values. That's the difference. When you do that change, you can increase, you will see, you can improve the rate of convergence. Did you understand the difference between Jacobi's method and Gauss-Seidel method? Did you understand the difference between these two? Yes. Yeah, let's compare these two. When you compare Jacobi's method and Gauss-Seidel method, yeah, you can see that Gauss-Seidel iteration converges more rapidly than the Jacobi iteration. Since it uses the latest updates. But this one is very important. But yes, there are some cases, some systems that Jacobi iteration does not, does converge, but Gauss-Seidel does not. Right? So you will encounter some linear systems. Some linear systems AX equal B. You can obtain solutions, approximate solution. You can, so you can. So you generate using iterative methods, you generate a sequence of approximations. So you will realize for some systems, right? Jacobi iteration converges, but Gauss-Seidel doesn't. So for some system, this is not for. So you cannot say, Gauss-Seidel always converges, or converges more rapidly than Jacobi's. For some systems, Yeah, for some system, Jacobi converges, Gauss-Seidel doesn't. Right? For some systems. Okay. So to accelerate Gauss-Seidel, you can improve this algorithm further. You can improve this algorithm further. Yep. So that is, yep. So this is your, yeah, Gauss-Seidel, right? Look at this. This is the previous iterative. This is the current iterative, right? This stage is the current iterative, K plus stage. And this is the previous iterative. And this is the correction term, right, in the Gauss-Seidel. Yeah, correction term. Yeah, so you can rearrange this to that. You can rearrange this to that. Yeah. So here, rearrange. You can rearrange here. So this is cancelled here. Yeah. So this is the correction term. Okay. All right. So previous solution, the current stage solution, and this is the correction term. Then you can introduce a small weight. You can weight these two terms. Can give a weight, right? Or you can add a parameter to these two to fine tune your solution. You can add a parameter like this here. Omega is a parameter. If you give us more weight on this, then you can accelerate the rate of convergence. If you add a parameter omega like this to the correction term, or you can add a weighted average, or you can add parameter like this. Yeah, you can fine tune this correction term. You can give more weight on this compared to the previous solution, right? So you can fine tune this parameter maybe. So you realize that when you play with this code, yeah, you will realize that you will get fast convergence whenever. So this parameter in between 1 and 2. Yeah, so if omega is in between 0 and 1, you don't see much uh, improvement of the code. Yeah, so algorithm is slow, you get slow, yeah, convergence. If you want to improve the rate of convergence, yeah, add the parameter omega and give a weight, yeah, between 1 and 2, then you will realize that this algorithm converges. Yeah, so when you generate a sequence using this algorithm, you will realize that this sequence converges very rapidly than or very fastly than the very faster than the previous Gaussian elimination. Can add a parameter like this. So this is the fine-tune parameter. So you can do a small research. Yep. So you can change this parameter value. You can put 0.5. What happened to the rate of convergence? Yeah. Like this, you can do a small research. Yep. So after we realize that after 27th or something. Yep. So this code Gaussian eliminate converges, right? So like that, you can do a small research by changing this omega. So you finally you will realize that so if omega between 1 and 2, so this your generated sequence converges very rapidly faster than Yeah, by doing trial and error. Yeah, so by doing trial and error. Yeah, so you can understand. Yeah, you can realize this parameter value. You realize that. Yeah, so if you give this much, that depends on the coefficient matrix. Yeah, coefficient matrix. Yeah, you had to do trial and error to realize the parameter value. Yeah, optimal parameter value. Right? Yep, like that, you can change the rate of convergence by introducing a small parameter here. Okay, so that is SOR method. So SOR is the most improved version of the Gauss-Seidel. Gauss-Seidel is the improved version of the Jacobi's method. Right? Okay. Yeah, so far we have discussed Jacobi's method, Gaussian elimination. No. What is this? Gauss-Seidel. Yeah, Gauss-Seidel method and SOR. So this is the most refined method, iterative method, right? So these are called stationary iterative methods. Here you don't change. Here you don't change the parameter. So this is fixed all the time. This is fixed all the time. But if you change, so these are non-stationary iterative methods. I think this course don't discuss these methods, non-stationary methods. So here, so if you look at these methods, these are variables, I think. So these parameters is change. These parameters are change all the time. So here, so these are change all the time. So this is the iterative equation. So this, look at this. This is the previous iterative and the current iterative, and alpha I here. So alpha depends on these values, and this is the residual. So this residual changes all the time. So these parameter values changes all the time. So these are called non-stationary iterative methods. This method is a non-stationary. So these are stationary methods. For these methods, the algorithm does not change. Not SOR. If you consider Jacobi's method, so this is fixed. This one also fixed. But SOR, when you change omega, this is it changes. The matrix changes. This is fixed, and when you so there's a parameter here, but it doesn't for the iteration this is fixed. If you select one parameter value, let's say 0.5, then for this parameter value you can generate the sequence, but so it is fixed. Then you can change this parameter value omega 0.6, let's say 1.6 or something, then you can generate another sequence. So that means this is stationary iterative method. But these are non-stationary. Why? So this alpha changes. So when you find the first iterative, right? So you have one an alpha 1. So the next alpha, so it change. it is change. So this is change. Yep. So this is non-iterative, non-stationary. Yep, iterative method. So this is yeah. So this alpha 2 is change. Alpha 3 different number. Alpha 4 again different. Yep. So because of this, but this omega is fixed for all for this sequence. Yeah, this is change. So yeah, these are non-stationary iterative methods. So these are not important, right? So in this session, I wanted to cover Jacobi's method and Gaussian elimination. No, Gauss-Seidel method. So this is the improved version of Gauss-Seidel method by adding a parameter omega, and these are non-stationary iterative methods, and these are stationary iterative methods. So if you have time, yeah. So I think fourth year, I think so you will learn these methods in numerical analysis if you major mathematics or if you do math special. Yeah. So in fourth year you will learn, yeah. So non-stationary iterative methods as well. All right. So any questions? Yeah. So I think yeah. So no time. It's almost 10 o'clock. Yep. So you can show that you can go through the this part, right? So this is the error. Error in the k plus 1 stage is less than norm of the error, right? Norm of the error in k plus 1 stage is less than, you can show that, yeah, the norm of this matrix E is, what is E? Is, yeah, is this matrix. You can rearrange this, yeah. So E is that matrix. So this is this is Jacobi E. So E matrix is this. And for Gauss-Seidel, what is the matrix E? Yeah, is, yeah, this one. And the other one is SOR. SOR, this is the matrix E. SOR, right? So you can show that, yep, so you can show that. So, yeah, so, yeah, so error in the k plus 1 stage, norm of error is less than norm of that matrix. That depends on the method you use, let's say Jacobi or any, yeah, so this changes, right, according to the method, right? E, yeah, e to the, yeah, e to the power k plus 1. Yeah, norm of this matrix times initial error. So you can, yeah, do this. Yep. So then you can show that, yep. So if the limit, norm of this matrix, limit of goes to 0 as k tends to infinity, then the error also goes to 0. Error. You can show that, just refer to this. That means you can show that the matrix is, yeah, so error is reducing to 0. Error is reducing to 0. That means your sequence converges to the exact solution. This error means, so this is a vector again. Yeah, so your error, norm of error, yeah, so approaches 0 as k tends to infinity. That means your generated sequence converges to exact solution. So what is the condition? This is the sufficient condition. Which one? Yeah, this one, Yep. So your coefficient matrix should be diagonally dominant. If your coefficient matrix is Strictly, this should be strictly because here no equal sign. Strictly diagonally dominant, then Jacobi or Gauss-Seidel or SOR converges for any initial guess. For any initial guess. So that's why I told you this theorem is very important. Then we can guarantee your generated sequence converges to the exact solution, right? If your matrix is strictly much better, see, strictly is much better, right? Without equal sign, right? Strictly diagonal dominant. If your matrix A is strictly diagonal dominant, then we can guarantee that your generated sequence of approximation converges to exact solution of this system for any initial choice. Okay, got it? If you want to impose a stopping criteria of your algorithm, you can check the norm of the residual. Let's say I will stop my algorithm when this norm of residual is less than 10 to the minus, let's say 5, right? Then I can impose this stopping criteria. So I have to so inside the if condition, so this I compute this norm of this residual is b right hand side minus a times your generated approximations kth stage. So you compute this, and if this is less than 10 to the minus, you can specify any number, if you won't get accurate solution, 10 to the 10, 10 to the minus 10. Like that, you can stop your algorithm. If this one is true, then stop, break, then get my approximate solution. Okay, like that, you can impose a stopping criteria, or you can, if you don't like to impose a stopping criteria, you can put, so here I execute 100 times, or you can execute 1,000 times. But it is better if you impose, or here I execute this code 100 times. If you impose this kind of stopping criteria, this is much better. So I always compute this residual and the norm of that residual. If the norm of that residual is less than this, then I get much better close solution to the exact solution. Okay, then I stop running this code. There's a for loop here. This for loop going from 1 to max now. So but you can impose this criteria if you like. Any questions? And so this is one of examples. So initial guess is 0, 0, 0. When you start off that initial guess, so this is the solution in first stage. So initially you have this much residual. In the first stage, you can see the improvement. residual norm of the residual is reducing. 26 now 10. In the next stage solution, second stage solution, what is the residual? 6. Okay, 1 point. Yeah, so I will stop my criteria when the residual is less than 10 to the minus 5. Yeah, so then you can uh, yeah, find solutions for other iteratives. Yeah, for other iteratives. Yeah, so matrix is divided into, yep. So this matrix, look at the matrix. Yep, so 4 is bigger than sum of magnitude. Yep, magnitude of minus 8 is 8. Yeah, so strictly diagonal dominant. Yep, so that theorem is true. Yeah, if it is strictly diagonal dominant, then we can guarantee that our generated sequence of approximation converges to the exact solution for any initial conditions. So, this is the initial condition. So you can see by computing the norm of the residual. So seems like converging. Reducing this residue norm of the residue. All right. Let's stop recording. For the session. So look at this matrix here, coefficient matrix. This matrix is not diagonally dominant. Why? Here, magnitude of this one is 2. The sum of off diagonal is bigger than the magnitude of the so this matrix is not diagonally dominant. So what happened to the residual? Oh my god. So initially we start with this. The residual at the beginning, the norm of the residual is 26. When you when you find the iterative, when you use Jacobi's iterative, I think Jacobi, we always use all solutions. 0, 0, 0. Yeah, this is Jacobi. Yep, so this is the solution in the first stage, x1, x2, x3. When you find the residue, norm of the residue, it is increasing. Yep, so if your matrix is not diagonal dominant, is not diagonal dominant, we cannot guarantee this generated sequence converges to the exact solution. We cannot guarantee. Yeah, residue. What happened to the norm of the residue? To 208. The residual term is increasing. Yep. So matrix. So if the matrix is not diagonally dominant, there is no guarantee that the generated sequence converges to the exact. It may converge, don't know, right? But if your matrix is diagonally dominant, strictly is much better. Strictly diagonally dominant. 4 is strictly bigger than sum of diagonal. Magnitude, always magnitude, right? 8 magnitude of minus 8 is strictly bigger than 4 plus 1. 5 is strictly bigger than 1 plus 2. Yes, this is strictly diagonally dominant. So then I can see, so our generated sequence converges to exact. So this is close to the exact solution than this. Okay, I hope this makes sense. If you